What's up, everyone? Welcome back to another lesson with the amazing Mr. A. Yours truly, ready to learn you some chemistry. Today, we're going to talk about percent yield, which directly continues from our last lesson of limiting reactants. But before we get into it, we got to dive into a couple key terms. First being percent yield. So, what percent yield tells us is essentially how efficient our reactant is. Our reaction is. And this formula that goes along with percent yield equals actual over theoretical yield. Let's just fill those in there. All right. So again, percent yield tells us how efficient our reaction is, or maybe our experiment, we can say. Experiment. And the way we do that is by comparing two values, an actual yield and the theoretical yield. So let's start off with the one that we know, but maybe we didn't know that we knew, the theoretical yield. The theoretical yield is what we have been dealing with all along. This is the yield calculated based on given information. Based on given info. So that's like we did before with our limiting reactants. For example, here we calculated the mass of sulfur dioxide in this question from last lesson. This grams of sulfur dioxide would be the theoretical yield for this problem. Theoretical meaning if all possible product is made. All right, so after you find the limiting reactant, find the amount of product made, what you're solving for is the theoretical yield. Now, in reality, when you're conducting these experiments and going through and trying to make whatever products you're making, there's a lot of side reactions, a lot of things that you cannot account for during a real experiment. That's where you get this actual yield from. The actual yield is the yield measured from an actual experiment. Okay, and this will be given to you in a problem. Okay, so we have a theoretical yield, which we have already been dealing with. It's something that we calculate based on the given information. And then we have this actual yield. The actual yield, again, is something that if we were actually doing this experiment, we could measure the amount of product made for whatever reaction, and we would know our actual yield from the experiment. However, when you're given questions on these percent yield topics and the stoichiometry problems, they'll just give you this actual yield. The question will say, what if the actual yield was this? What's our percent yield for this experiment? And we'll get into a problem right now dealing with that. So here we have an example reaction. Formation of methanol from carbon monoxide and hydrogen gas. Already balanced the equation for us. Let's just go ahead and write that over again so it's nice and big. Oops. Alrighty. Now, in these questions, you'll see that A and B might look familiar because those are from our limiting reactant lessons. C should look familiar. The only thing that's different is this theoretical yield key term. That being said, you have actually already been finding the theoretical yield without knowing it's called the theoretical yield. So let's just go through these problems here. And then I'm going to add a part D at the end just to tie in our percent yield. So in question A, it says if you start with 5 moles of carbon monoxide and 7.5 moles of hydrogen gas, what is the limiting reactant? All right, so we have 5.0 moles carbon monoxide, 7.5 moles of H2. So we have our two reactants, and what I'm going to do is figure out, well, how much moles of methanol can each one of these make theoretically? Just tying in some keywords there, don't mind me. So what I'm going to do is set up both these questions with a mole ratio. Oops, let's not forget about the number values. A mole ratio comparing methanol with either one of our reactants. So for carbon monoxide, 1 mole methanol for 1 mole carbon monoxide, and for hydrogen gas, 1 mole methanol, 2 moles of H2. Cancel out the like units. Everything should be in units of methanol, moles of methanol. And right here, let's just get a 5.0 moles of methanol. And down at the bottom here, I think that's 3.75 moles of methanol. So comparing these two, we can see that this right here is the least amount of product made, which means that 7.5 moles of H2, 7.5 moles H2 is the limiting reactant. And that would be our answer for part A. Easy does it. So far so good, nothing new, right? There should be nothing new if we did the limiting reactant lesson first. So moving on to part B. How many moles of excess reactant are present? So part B, how many moles of excess reactant are present? Well, since we determined that 7.5 moles of H2 is our limiting reactant, we know that 5.0 moles of CO is our excess reactant. Now we need to figure out, well, we know we're starting with this much. We have to use some amount of it in order to make this reaction take place. And then since we're not using all of our 5.0 moles of carbon monoxide, there's going to be some left over. So what we're going to do is, using our limiting reactant, figure out how many moles of carbon monoxide we used. And we're going to do that by using a nice mole ratio. And that's going to be 1 to 2. So 1 mole of carbon monoxide for 2 moles of H2. And we should get 3.75. So this is how much we used. So we're going to take the given minus used will equal leftover. So we were given 5.0 from right here. We used 3.75. And by my calculations, that means we have 1.25 moles of carbon monoxide in excess. Let me put some space there. Alrighty. So that's our answer to part B. How many moles of the XX reactant do we have? We have 1.25 moles of carbon monoxide excess. All right, sweet. So that was cool. That was fun. Let's move on. Part C. What is the theoretical yield of the reaction? The mass of the product that will form. All right. So remember, theoretical yield. That's our new key, one of our new key terms from today. But it's nothing that we haven't dealt with before. So theoretical yield, again, is the amount of product made that we calculate. So in order to calculate that, we're going to use this portion right here. The reason that I'm choosing this portion right here is because we know that this is our limiting reactant, and our limiting reactant dictates how much product we can make. So our limiting reactant is making 3.75 moles of methanol. All right, and that's, again, remember there was two different approaches for finding limiting reactant. Again, I choose this way when we're dealing with the product because it's going to make this part C much faster. Because all we need now is the molar mass of methanol. All right, we could look that up, and we'll see that the molar mass is 32.04 grams per 1 mole. Cancel out the units, showing that because we are good students, and we could find that we have 3.75 times 32.04, 120.15 grams of methanol. And this is our theoretical yield. Boom. All right. So what we found is that theoretically, this reaction can make 120.15 grams of methanol. Wonderful. Now, let's say in this question, like I said earlier, I'm going to make a part D. So let's say part D, and with part D, it says after an experiment, it is found that the actual yield for methanol in this reaction is, I don't know, let's just say it's 60.75 grams. What is the percent yield of this experiment? All right, so if this question was dealing with percent yield, you would see some kind of question similar to the one I've written down. Now, again, percent yield, right? A percent yield, we said that it tests or it shows how efficient our experiment is, right? How efficient our experiment is, because it's a comparison to what we could have got theoretically versus what we actually got in a lab. And in our example here, theoretically, we could have made 120.15 grams of methanol. And in the lab, in the experiment, you followed all the procedures, and for some reason, you got 60.75 grams instead. And that could be due to many things, maybe some side reactions, maybe some, I don't know, some spillage. A lot of human error can be possible. So we're just trying to figure out if we did this experiment over and over again, we kept getting similar numbers. Is it really that efficient? Well, let's look at the percent yield and determine that. So all we have to do is use our percent yield equation, which is percent yield equals actual over theoretical. And since this is a percentage, we'll just remember to multiply by 100%. Alrighty, so now just plugging in what we know that our actual yield, it was given to us, 60.75 grams. And our theoretical yield is what we calculated earlier, 120.15 grams. And in doing this 60.75 divided by 120.15 gives us, and times 100, 50.6%. So the percent yield of this experiment is 50.6%. All right, so it tells us again, is this good? Is this good? And well, it kind of depends on what scale you're looking at. So typically, 80% is considered very, very good. So 80% is very good. 70%, that's good. 50% fair. And pretty much anything below is poor. All right, I guess if you guys were getting graded on this scale, you'd be at least good for the most part. Now, these are just some percentages that I found online. In different textbooks, it might change. Typically, I'll see probably like a 60% cutoff is what I remember from the book I was using in my class. 60 and above, good. And I guess it should be 59 and below, bad. So if we were using this scale instead, comparing here, we can say that this is a bad or poor yield. So that tells us that our experiment, something's wrong with it. We need to fix something with this experiment because we're wasting a bunch of stuff. Right? Now, one question that might come up is, well, can we get a percent yield equal to 100%? Is it possible that an actual yield is exactly the theoretical yield? And no, not possible. Ideal? Yeah, but it's not possible. We can approach up to 100%, but we cannot get there. There's too many factors to consider. Unfortunately, we'll never be perfect. But I guess, that kind of just has a nice spin on life. Even if you tried and tried and tried, nobody's perfect. We're all flawed beings. That's what we get for being human. Am I right? Anyways, I hope you enjoyed another wonderful lesson with yours truly, the amazing Mr. A. Hashtag Mr. A, hashtag amazing, hashtag, whoa, I just learned some chemistry. If you feel so inclined, please go ahead and like, subscribe, and hit the wonderful bell so that way you know every time I'm putting down one of these hot vids. Until next